Welcome back, everybody. We're diving deep today into the world of powder metallurgy. Specifically how we can make some pretty amazing things out of metal powder. We've got 3 research articles to look at today, 2 from Turkey and 1 from an international journal. They might seem kind of unrelated at first glance, but stick with us here, and I think you'll be surprised how they all connect.
Yeah, it's a field that's really changing what's possible with metals.
Yeah.
We're talking about creating super complex shapes and even changing the properties of the metals themselves, like at a microscopic level.
Okay, so let's jump right into this first article from Turkey. The researchers here were essentially trying to supercharge stainless steel using something called powder injection molding, or PM.
You can think of it kind of like those plastic injection molding machines. But instead of plastic, we're injecting a mix of fine metal powder and a binder material. PM lets us create really intricate parts with incredible precision. These researchers were working with AISI 420 martensitic stainless steel. Now, martensitic refers to a specific crystalline structure that makes this steel incredibly tough and corrosion resistant. It's used in everything from knives and surgical tools to aerospace components.
So we're talking about taking something that's already pretty tough and making it even tougher. How did they do that?
They added a pinch of niobium, or Nb, on the periodic table. Niobium is a pretty amazing element. It can seriously boost the strength and durability of steel.
Wait, so just adding a tiny bit of niobium can make a huge difference? I'm picturing it like adding a secret ingredient to a recipe that suddenly makes everything taste way better.
That's a great analogy. And here's how it works on a microscopic level. When you add niobium to the steel powder mix and then heat it up during the sintering process, the niobium reacts with carbon in the steel to form tiny, ultra-hard particles called NBC precipitates. These precipitates act like tiny anchors within the steel structure, making it much harder to break or wear down.
So you're saying that these tiny anchors can make the steel almost 50% stronger? That's incredible. It's like turning a regular bicycle into a mountain bike. Did they find anything else interesting in their research?
Absolutely. They found that the environment you bake the steel in also plays a huge role. They tested sintering the steel in 2 different atmospheres, argon and hydrogen. It turns out that using hydrogen resulted in significantly better mechanical properties and corrosion resistance compared to argon.
Okay, so it's not just about the ingredients, but also about how you cook them. Why does hydrogen make such a big difference?
Well, hydrogen is excellent at removing oxides that can form on the surface of the metal particles during sintering. Those oxides can act as barriers, preventing the atoms from bonding together properly. By getting rid of those barriers, hydrogen helps the particles bond more effectively, resulting in a denser and more robust final product.
This is making me realize just how much control we have over materials at such a tiny level. It's mind-blowing. And speaking of control, this incredible precision makes me think about the challenges of creating intricate shapes. Which brings us to our second article from Turkey.
Yeah, these researchers were tackling a pretty tough challenge. Even with traditional methods, we have trouble creating internal screw threads within metal parts without using complex and expensive molds.
Yeah, I can see why they went for this. Internal screw threads are notoriously tricky to make. How did they even approach this?
Well, their approach was pretty clever. They used inserts that already had preformed screw threads and tried to mold the metal powder around them. The trick was to coat these inserts with special materials to prevent them from diffusing into the surrounding metal powder during sintering. It gets really hot, remember?
So it's like trying to create a perfect mold of the screw threads inside the solid metal? What kinds of coatings did they use for this?
They experimented with 2 different coatings. Chromium, a metal known for its high corrosion resistance and good diffusion barrier properties, and hexagonal boron nitride, which is a ceramic material that's incredibly stable at high temperatures and has a structure known to inhibit diffusion.
So did it work? Were they able to create those internal screw threads without those complex molds?
Well, this is where things get really interesting and a bit disappointing. The experiment didn't go quite as planned. Despite the coatings, diffusion still happened between the inserts and the surrounding metal powder during sintering. And this messed up the screw threads, making them unusable.
Oh man, it's like they were so close to a breakthrough. This actually makes me think about the time I tried to build a bus shelf and completely stripped the screws. It's crazy how something so small can cause such a big problem.
Yeah, it definitely highlights how important it is to understand all the factors that are at play. And it connects really well with our third article, which might seem totally unrelated at first. It's all about this complex dance between a material's properties, the stress it's under, and the environment it's in.
You know, when we first added this article to the stack, I was kind of scratching my head. It's about environmental stress cracking in plastics, which seems pretty far from making metal parts, right? but I'm curious now to see where you're going with this.
So the article focuses on this phenomenon called environmental stress cracking, or ESC. It's basically what happens when a plastic that seems durable suddenly fails under stress when it's in specific environments. Think of a sturdy plastic container that holds up perfectly fine under normal conditions, but then cracks when it comes into contact with a certain liquid.
Okay, I think I see the connection now. Just like with the screw threads, you've got all these different factors interacting with each other, and if you don't understand how they work together, things can go wrong.
Exactly. And this brings us back to the metal powder research. In the first article, the choice of sintering atmosphere, whether they used argon or hydrogen, had a huge impact on the final properties of the stainless steel. And in the second article, the researchers were trying to control the diffusion between the inserts and the metal powder during sintering. It all comes down to understanding how these materials behave under different conditions and how they interact with each other and their environment.
So it's not just about finding the strongest metal or the most heat-resistant coating. It's about understanding the whole system, the material, the process, the environment, and how all these factors influence each other. It's like this delicate balancing act.
Exactly. Going back to those failed screw threads, maybe the coating wasn't the only problem. Maybe the sintering temperature or the specific composition of the metal powder also played a role in the diffusion that messed up the screw threads.
That's a great point. It really shows how a seemingly unrelated field like polymer science can help us understand challenges we're facing in metal processing.
Absolutely. And this unexpected connection highlights a broader perspective that's really important for anyone working with materials. Whether you're shaping plastics or making high-performance metals, a deep understanding of how materials behave is essential.
This is all super fascinating, but let's bring it back to the listener for a second. What does all this mean for someone who isn't a material scientist or an engineer? Why should they care about these details of metal and plastic behavior?
Well, for starters, it affects the quality and reliability of the products we use every day. From the cars we drive to the medical devices we rely on, understanding material behavior is essential for making sure these products work as expected and don't suddenly fail.
So it's about safety and making sure things work the way they're supposed to. That makes perfect sense.
It's about safety and making sure things work the way they're supposed to. Absolutely.
Yes.
But it also goes beyond that. It has implications for sustainability and resource efficiency. By carefully selecting and processing materials, we can create products that last longer, require less maintenance, and have a lower environmental impact.
Those are some really compelling reasons to pay attention to what's happening at the microscopic level. So where do we go from here? We've explored these 3 fascinating research articles, uncovered some unexpected connections, and pondered the mysteries of those failed internal screw threads. What's the final takeaway for our listeners?
Okay, well, let's recap what we've learned today in our deep dive into the world of metal powders. First, we saw how adding just a tiny bit of niobium can significantly increase the strength and corrosion resistance of stainless steel.
It's like giving the steel a superpower.
Exactly. Then we learned that creating internal screw threads without complex molds is still a big challenge, even with some really clever approaches.
Yeah, it's a good reminder that even the most brilliant ideas sometimes hit a roadblock.
For sure. But those roadblocks often lead to even more exciting discoveries. And that brings us to our third article, which highlighted that fascinating phenomenon of environmental stress cracking in plastics. Who knew that plastics and metal powders had so much in common?
Right. It just goes to show that seemingly unrelated fields can offer valuable insights into each other. The key takeaway here is the importance of understanding how materials behave in different environments and under different stresses.
Yeah, and how all those things are connected, the material, the process, the environment. It's about understanding the whole system.
Before we wrap up, I want to circle back to those failed screw threads. Do you think it's a problem that can be solved? Is there a way to create those internal threads without relying on complex molds?
I definitely think it's solvable. It's just a matter of finding the right combination of materials, processes, and really understanding those tiny interactions. Maybe a different coating material would do the trick, or maybe we need to explore completely new approaches.
This makes me think about how nature builds incredibly intricate structures. Think about the spiral of a seashell or the honeycomb structure inside a beehive. Nature has been solving these kinds of engineering challenges for millions of years.
That's a great point. Nature is an amazing engineer, and there's so much we can learn from its designs. Maybe the key to creating those perfect internal screw threads is by mimicking a natural process.
That's a really inspiring thought. It seems like the possibilities are endless when we start thinking outside the box and looking to nature for inspiration.
Absolutely. And for our listeners, I encourage you to keep exploring these ideas and challenge yourselves to think creatively about how we can push the boundaries of materials, science, and engineering. Who knows, maybe you'll be the one to crack the code of those mold-free internal screw threads.
And on that note of inspiring innovation, we'll wrap up this deep dive into the fascinating world of powder metallurgy. Until next time, everyone stay curious and keep exploring.